Alright. Hello everyone. Today I would like to teach about second order circuit. This is notes, PowerPoint notes in part 2. So in part 2 we will look into the source-free parallel RLC circuit. The first thing we need to look into is the timeline. Okay, so remember in chapter 2 we always do the timeline whenever you see a switch appeared in the circuit. So for each of this timeline, so let's say at t equals to 0 negative, this is just before a switch is open. At t equals to 0 positive is just after a switch is open or closed. And as t goes to infinity, this is the long time after a switch is open or closed. So for each of this timeline, what you need to do is to redraw and look into the circuit so that you can analyze it better. So for each of this timeline, please redraw your circuit. Okay, because normally the circuit will look different at these 3 times. So you'll need to redraw it anyway, right? So this part is important. All right, let's look into the natural response of source-free parallel RLC circuit. You are given a source-free, meaning that there is no external voltage or current inside this circuit. So you only have RLC connected in parallel. We can do the analysis by using mathematical equation with differential equation Vt instead of It, because now we are sharing the voltage. Remember that parallel elements share the same voltage instead of the current. Okay, so we also define the Neper frequency or alpha to be equal to 1 over 2 RC instead of R over 2L. R over 2L is used in a series connection circuit. So in the parallel RC circuit, we may find this in many practical applications. Most of them is in the communication networks and filter designs. Okay, so let's consider the circuit in figure 3. The analysis that we want to look into is actually using the KCL. Okay, so the energy is represented by the initial capacitor voltage appeared at the capacitor. Okay, and we also look into the initial inductor current I0. Okay, this is the initial condition for voltage and current at the capacitor and inductor. Okay, so I0 is the initial current at the inductor using this equation, and V0 equals to capacitor voltage, initial capacitor voltage taken at the capacitor. Okay, then we apply KCL at the top nodes and it gives you the current. This is the current for resistor, this one is the current for inductor, and this one is the current for capacitor. Okay, so looking at this equation, you see that this one is derivative, this one is integral. So you need to solve the equation to make sure that you have a similar parameter. Okay, so taking the derivative with respect to t and dividing the equation by c, this results in equation 29. So now only you can see that there is a second order differential equation appear in the solution. Okay. Since this is a second order circuit, we want to replace the first derivative. So this one is the first derivative, dv over dt, and this one is the second derivative by s squared. Okay, so by looking at this, we actually comparing these two, you substitute the second derivative by s squared and the first derivative by s, so you get the equation 30. Okay, next, the roots of the characteristic equation. Since we have a quadratic equation, so normally you can find the roots, two roots, S1 and S2 by using this equation. Okay, this is minus 1 over 2C plus minus set 1 over 2 RC squared minus 1 over LC. And if you compare this in to the series RLC circuit, this one is actually the minus alpha plus minus set alpha squared minus omega naught squared. All right, where your alpha is no longer R over 2L, but it is now 1 over 2 RC, and your omega naught is still the same. Okay, by applying KCL and some algebra, so we get this. And assume the form of the solution for this second order derivative should be in the terms of a exponent st. So this one is natural solution, always using exponential. Okay, so we can derive the characteristic equation by equating this to 0. Okay, so for convenience, we define your alpha equals to 1 over 2 RC and omega naught equals to 1 over LC. Note that your omega naught is the undamped natural frequency, and this is the same with your series RLC circuit, but the Nepal frequency, your alpha is different. Okay, just as for series, you will have this equation is equal to s squared plus 2 alpha s plus omega naught squared equals to 0. And now you can get the three cases like in series RLC, which is the overdamped case, the critically damped case, and the underdamped case. Okay, the first one is the overdamped case where your alpha is greater than omega naught. So it's a good check by using alpha greater than omega naught, and you can always check your elements. If your L is greater than 4 times R squared times C, this one normally gives you an overdamped case. Okay, so you can always solve your solutions. You can always solve your roots S1 and S2 using this equation. Normally, it gives you a distinct negative real number. In this case, the solution to our differential equation is Vt equals to A1 exponent S1t plus A2 exponent S2t, meaning that you need to solve your A1 and A2 constant by using the initial condition determined by your initial voltage and also your dV naught dt. Okay. In the critically damped case where your alpha is equals to omega naught, we will have two solutions for your roots. Your S1 and S2 should be equal to each other, and both are equals to minus alpha. So in this case, the solution to our differential equation will be A2 plus A1t exponent minus alpha t. Then, since you have two constant A1 and A2, we will determine these values using the initial condition for V naught and using dV naught plus dt. In the underdamped case, where your alpha is less than omega naught, this one will give you S1 and S2 a complex numbers. Complex numbers means you have a real number and an imaginary number. Okay. Here J is the imaginary unit and your omega d is called the damped natural frequency. And now your solution for differential equations become exponent minus alpha t times b1 cos omega t omega dt plus b2 sine omega dt. Okay. Again, you will need to solve your b1 and b2 using the initial condition v0 positive and dv naught positive dt. So if you compare the three cases, the graph of the three cases is look like can be plotted like this figure. So you have overdamped case, the black line. The critically damped case is the red one, and underdamped case is the blue one. So you can see the oscillation at the underdamped case because you have cos and sine solution. Okay, by looking at this also, you can compare which of these solution will give you the fastest time to settle down or to reach the steady state time. Okay, I show you the general approach to solve your source-free RLC, whether it's series or parallel. So the first one you need to do is to find the quantity's initial value. X here could be your current or could be your voltage. So the first thing you need to find is your initial value, which is I0 negative and V0 negative. Okay. The second step you need to do is to find the quantity's initial derivative, dx0 positive dt. Okay, so dx here could be your dv0 positive dt or di0 positive dt. The third step is find the Nepal frequency. Okay, for alpha is alpha equals to R over 12 in a series RLC, while for parallel RLC, it gives you alpha equals to 1 over 2 RC. The first step is to find the undamped natural frequency, which is omega naught equals to 1 over Z LC. And number 5, you compare these two, alpha and omega naught, to identify which type of solution you need to work on or you need to analyze. Okay, so let's go to the step 6. Okay, in the case of overdamp, where your alpha is greater than omega naught, so you need to find two roots, S1 and S2. Okay, and then you need to solve A1 and A2 by using the initial condition, and you can solve your A1 and A2 using this one. In the step 7, in case of critically damped case, your alpha is greater than omega naught. So again, you use initial condition to solve your A1 and A2, and then you can substitute it into this general solution for critically damped case. For underdamped case, where your alpha is less than omega naught, then your omega d should be equals to omega naught squared minus alpha squared, and you will have B1 and B2, and then you solve it using the initial condition Bx 0 positive and Dx 0 positive, and then you substitute this into the general solution of underdamped case.